In this module, we're going to review what is VLSI. And first of all, what does that stand to begin with? Well, VLSI means very large-scale integration. And to understand what that means, I propose we go through a little bit of history of computers. Well, we could trace back computers as early, obviously, as the discovery of electricity with a volta cell and then all communication means with Morse telegraph, telephone, and more importantly, the invention of the first vacuum tube. The first vacuum tube enabled active electronics and therefore active operations, which was the basic for creating a calculator. In 1946, this machine called ENIAC was actually the first computer, and it was built around 17,000 vacuum tubes and 1,500 relays. It was weighing 30 tons and was burning 150 kilowatts of power. Can you believe that? 150 kilowatts of power. That's to be compared to the power consumption of a bulb, which would be 100 watts for incandescent light. And this was only doing 5,000 additions per second. Needless to say, this was still a very important machine and opened a complete new field. Now, what could have revolutionized these calculators? Well, this has been the introduction of the germanium transistor, 1947, leading to the Nobel Prize for these three gentlemen. From the germanium transistor, things kept evolving with the first silicon transistor in 1954, and the first integrated circuit putting effectively resistors, capacitors, and transistors all on the same substrate and not as a single device. From there, 1959, planar integration, which is the invention of the microelectronics, and the realization of the first MOSFET that is still the current basis for our electronic systems. I'd like to point out one thing. This was 10 years prior to Apollo 11. People went actively on the moon without having one memory, 1972, the first DRAM memory from Intel, and 1971, the first microprocessor from Intel. So all the calculators and computers were actually built out of glue cells or standard logic cells and not actively integrated microprocessors. Pretty impressive, huh? Now, since the invention of the first microprocessor, things have been evolving and people experience an evolution of scaling. Here's an illustration of the first microprocessor, the 4004 from Intel in 1971, and its successor the next year, the 8008. I'd like you to look at the layout figures as well as the clock speed and number of transistors. So what you can note on these two devices is that the current line width, which is a technology node, was the very same. And how did people go about improving the performance of the system? It was to put more transistors, meaning larger functionality. In this particular case, it was increasing the bit width of the processor and also increasing the clock speed. But very quickly, what started to take off was scaling. Being able to cram more devices on the same chip while increasing the clock speed for the same power budget. And this is what I've been following after that with the 8080 processor, a very famous processor, followed by the 8086. As you can see right there, clock speed increased, number of transistors increased, line widths reduced. And that was a way, a fairly, I would not say an easy way, but a very convenient way to keep improving the performance. This has continued across the 80s and 90s with the 8088, the 286 processor from Intel. Again, number of transistors do increase, current line width reduces, and you get better performance out of it. It somehow, it continued, of course, with the 386, the 486, and so on and so forth. You will realize that now the complexity in terms of transistors is going above the million, and you will see that now the processor is also much more structured with the introduction of local cache memories and better general organization for the data paths and so on and so forth. Continuing there with Pentium Pro, you will, and Pentium 2, what you will see right here is that all of a sudden, for the same technology node and the introduction of the exact same number of transistors, we have a new family of processor, in that case, the Gaillardon processor, which was the reduced cost version of the Pentium 2. Same technology node, but now we see the market starting to introduce different products that would respond to different needs. Continuing with Pentium 3 and Pentium 4, you see again the complexity increasing and so on and so forth. What I'd like to point out now is that you see with the clock frequency of the Pentium 4, it was 1.5 gigahertz. I'd like to invite you to think about what's the actual clock speed of a modern microprocessor. It had definitely not increased significantly. You see from 1999 and 2000, it tripled, but the clock frequency has not tripled more and not really been beyond that in 20 years. So there has been now a slowdown that you could see starting from the year 2000. And that is the effect, the effective end of scaling per se. Reducing the transistor sizes to lower and lower dimension was not bringing the same performance increase, but instead was creating increases in leakage, thermal problems, and so on and so forth, precluding people to just go with this easier route of scaling. So how to cope with that? Well, it's been introducing tricks on the architecture level. Here are a couple of examples. The introduction of the Intel Atom and the Core 2 Duo. On the Core 2 Duo, you can see that this was one of the first multi-core processors. You have two independent cores that share a common cache memory. And that was a way to start introducing parallelism and to start increasing the performance of the system. The Intel Atom was introduced as an alternative compared to very high performance processors, but rather low power processors. And the Intel Atom was quite a remarkable piece of hardware at that time with several power consumption mitigation techniques using dynamic voltage and frequency scaling to adjust the power consumption to the need of the processor. Now, since we opened the door of going with multi-core processors, it naturally followed with the i7 processor series that introduced more multi-core processor, smarter acceleration, smarter techniques, and so on and so forth. This is what we still have in place today. Of course, we are now at almost the 10th generation of processor and keep evolving. Now, all of that was captured very well by the so-called Moore's law. Gordon Moore was a person from Intel who was able, at the very beginning of the semiconductor revolution, he was able to capture what the market is going to be and what the scaling evolution is going to be. And Mr. Moore predicted that the number of transistors on a chip will double every 18 months. This has been proven correct. Even until today, we're experiencing a slowdown, but that has been proven for several decades, and that's quite impressive. Now, to help you grasp better what is going on here, I'd like now to show you again the difference between the Intel 4004 and the Intel Pentium 4. They were all spaced by 30 years, and as you can see, if you look at transistors, frequency, and technology nodes, you can see an 18,000x increase in the number of transistors, 18,000x increase in the frequency, and a 6,000x reduction in dimensions, minimum dimensions, which is truly remarkable. And I'd like to, make a parallel with the other two industries that are part of the Industrial Revolution, namely the car industry and the aeronautics. If you apply the same scaling rules on the car industry, cars should be going at 3,000 kilometers per second with a mileage of 1 liter per 100,000 of kilometers, weight only 10 milligrams, and cost $20. Similarly, for aeronautics, a flight between New York and Paris should take a quarter of a second and cost only 1 cent. That never happened, of course, but I'm pretty sure that will help you appreciate the evolution and the degree of refinement of microelectronics. As I said, so unfortunately, Moore's law had some limits that were hitting pretty hard we've been hitting pretty hard for the past 10 years. MOSFETs do have physical limits. They suffer from leakage current. They have quantum behaviors at advanced dimensions, and they suffer from an increasingly higher level of variability, effectively making things more and more complex to reduce transistors' size even further, even though we're, of course, coming into production with a 3 nanometer technology node very soon, but it was not coming at a low price. Now also, as I said, economic limits. Economic limits coming from mass costs. It costs an enormous amount of money to make a new ASIC design because of this mask fabrication, and the fab cost as well. When a new technology node is created, the manufacturers, the foundries, are creating a new production unit for that, and that costs enormous amount of money as well. So now, what did Moore laws enable? Well, in the 70s, the Apollo program, for example, board-level integration was the key, where on a single board, you would put various packages that would contain memory, processor, general logic, peripherals, and so on and so forth. Since then, and the capability to integrate more and more systems on a single chip, we moved from board-level integration to the ASIC era. The ASIC era was to have more complex systems available on our chip, but still requiring to put all those functionalities together at the board level. I was, for example, putting a RISC processor with a DSP coprocessor and an FPGA, for example, to replace the glue logic. Now, since the years 2000 has come the system-on-chip era, where now the integration is at such capability that you can put every single function on a single chip in the form of what is called silicon IPs, where you'll have IP blocks that can be implemented and reused across various system-on-chip designs. And you will find a single chip that will contain a DSP core, that will contain a processor core, various input and output systems, complete video encoders and decoders, for example. Plenty of microcontrollers are like that. Fancy microprocessors and FPGAs are doing exactly that. And that's what is called the very large-scale integration. Very large-scale integration of transistors to enable the very large-scale integration of functions on the same chip. This class is about digital very large-scale integration. The market is ruled by digital circuits. More than 80% of the chips are digital in the market, and this is what is part of the system-on-chip design era. In order to design such complicated systems, you need for highly hierarchic and automated design methodologies. And this class will cover exactly that. We will cover digital VLSI circuit design, understanding how to build those circuits and how they're actually made of, what they're actually made of. And equally importantly, we will cover the EDA tools, so the complex machinery that you need to put together to design those actual beasts.